Hi, welcome to Gases Part 1. My name is Dr. English, and today we're going to be talking about the properties of gases. Specifically, we're going to look at the nature of gases, the kinetic molecular theory of gases, behavior of real gases, ideal versus real gases, Avogadro's hypothesis, and a little bit of practice at the end. So let's start out by talking about the nature of gases. Gases are defined as the phase of matter that has no definite shape or volume. They take the shape and the volume of their container. So if you have a plastic bottle, the gas that's inside that bottle is taking the shape of that bottle. They can expand or be compressed. In other words, are elastic. So like a balloon can either expand or you can, if the balloon's tied off, you can compress it and make it smaller. And that's all properties of gases. Gas volume depends on four different factors: the amount of gas, the volume, temperature, and pressure. And we look at pressure as caused by collisions of gas molecules with the walls of a container. Kinetic Molecular Theory of Gases, KMT, a set of agreed upon assumptions about the behavior of gases in order to more easily understand how they behave. All gases are composed of individual particles or molecules, or in some case atoms, that are in continuous random motion. The particles move in random, constant, straight-line motion until they are deflected by some force. That is, until the gas molecules hit the wall of a container or another gas molecule. Collisions that occur between gas particles may result in a transfer of energy from one particle to another, but the total amount of energy in a system will remain constant. The particles are so far apart that the volume of an individual particle is insignificant compared to the volume of space they occupy. So in other words, gas particles are really, really tiny. The last thing that we realize from the kinetic molecular theory of gases is that the gas particles have no attraction for each other at all. So in an ideal situation, they are not going to have any type of force of attraction. No intermolecular forces will occur between those gas particles. So an ideal gas is defined as a gas that meets the following four criteria exactly, no deviation whatsoever. Ideal gases remain gases under all environmental conditions. Now, real gases do not fit the kinetic molecular theory model exactly because real gases are going to have a small but significant volume, and they are going to have some attraction for each other based off of intermolecular forces. Environmental conditions influence whether gases follow real or ideal behavior. Real meaning they have volume and attraction for each other. Ideal meaning that they basically have no volume, it's really insignificant volume, and no attraction for one another. Conditions of low temperature and high pressure cause the ideal gas behavior described in the kinetic molecular theory to break down. So we got to make them really cold, and we got to force those gas molecules really close together. Under those conditions, gases will suddenly become liquids. One, because as you're slowing them down, they're getting really close together. And as soon as they become really close together, intermolecular forces kick in, and we can have dispersion forces or dipole forces occurring in between them, potentially hydrogen bonding, depending on the type of gas. London dispersion forces are weak intermolecular attractions will come to exist between individual molecules producing the liquid state. Ideal versus real gases. Gases behave most like an ideal gas following the kinetic molecular theory under the following two conditions: low pressure and high temperature. Under these conditions, the attractive forces are intermolecular forces among the particles will almost be non-existent, and the volume will be negligible in relation to the container volume. At STP, standard temperature and pressure, which you can find on Table A, hydrogen and helium gas come closest out of any of the gases to exhibiting ideal gas behavior. So those are the two gases that we really look at as being the most ideal. Avogadro's hypothesis. All gas molecules act as if they are the same size. Avogadro's hypothesis states that equal volumes of gases at the same temperature and the same pressure contain the same number of particles, in other words, molecules. So if you have gases that are at the same temperature and same pressure, no matter what the gram formula mass, no matter what type of the molecule it's going to be, we can assume that in that particular container, the same number of particles will exist. So here we have three different gases. We have carbon monoxide, we have hydrogen gas, and we have argon gas. If we look at the pressures here, the pressures all exist at 10 kilopascals. The volume is all the same, 5 liters, 5 liters, 5 liters. The temperature is all the same, 800 Kelvin, 800 Kelvin, 800 Kelvin. Therefore, no matter what the gas particles are, if the pressure, the volume, and the temperature between these three containers are the same, the number of the particles of each of these can be assumed to be exactly the same under Avogadro's hypothesis. Each of the three containers above in the accompanying diagram hold the same number, N, of particles, even though there's a different gas in each container. And we just went over what to look for in order to make that assumption true. Now let's do some practice together. The table below shows data for the temperature and pressure and volume of 4 gas samples, gases A through D. Which two samples have the same total number of molecules? So what we're looking for is 2 samples of gas that are at the same temperature, the same pressure, and the same volume. So we either have a temperature of 100 K or 200 K. Now we'll look at the 100 Ks first. So 100 K, 100 K, pressure here. Is the pressure the same? 2 and 2 atmospheres, yep. And is the volume the same? 400 and 400. So because these are all the same between these two samples, that will be our correct choice. So we just got lucky. So A and C, that's the correct answer. A and B wouldn't be correct because they're at different temperatures. B and C would not be correct because, again, they're at different temperatures. B and D, they start off looking the same at both being 200 K, but then we see that this is 2 atmospheres, this is at 4 atmospheres, so that's not going to work. In order for this assumption to be made, they all have to be at the same temperature, the same pressure, and the same volume. Let's look at another example. Which rigid cylinder contains the same number of gas molecules at STP as a 2-liter rigid cylinder containing hydrogen gas at STP? So the conditions here are STP. We're assuming 1 atmosphere. We're assuming 273 K for each of these. All we can really look for is something else that's in a 2-liter cylinder, no matter what the molecule is, because we're assuming that if it's an ideal gas, the number of molecules will be the same no matter what the gram formula mass of each of these gases are going to be. Therefore, the only other answer that is also 2 liters is B. So 2-liter cylinder of methane would be our correct choice in this particular situation. So what did we learn in this tutorial? We went over the nature of gases, we went over the kinetic molecular theory of gases, the behavior of real gases, which is an important thing to understand, ideal versus real gases, Avogadro's hypothesis, and a little bit of practice at the end. Need more help? Feel free to contact me. Have a great day.